Good afternoon, everyone. My name is Zhuo, and I'm a postdoc doctor at Norwegian University of Science and Technology. Today, I will present this topic, evaluating quasi-static and fatigue performance of lattice structures and the impact of scale and unit cell size and wall thickness. I would like to take this moment to thank all my collaborators to finish this work. And for this talk, I'll first introduce a bit about the background and the motivations, and then comes with some materials methods, and then the results and discussions, and finally the conclusions. So first, I'll start with the background and the motivations of this work. So as we all know, AM technology has been used in numerous fields, from small to large scales, such as biomedical implants, automotive, and the components and the constructions. It has a lot of advantages. For example, the freedom of the designs and the waste minimizations, and it has ability to fabricate complex structures such as lattice structures. And also it can consolidate assembly into the single part and as well as the fast prototyping. But at the same time, it also has multiple drawbacks, such as the surface roughness will significantly impact the fatigue properties, and also the fabricated specimens has geometric deviations compared to the design files, and also it has the internal porosities which can affect the mechanical properties as well. So that's why the aim for this work is to investigate the scales, wall thickness, and the unit cell size effect of the mechanical properties on the lattice structures under both quasi-static and cyclic compressed loading conditions. So why are we so interested in this aim? First, because the various scales of the lattices have a great potential applications, and the different scales of the lattice can correspond to different geometric deviation because of the fabrications, and also this will include the static and fatigue properties. And also there is a huge research gap for this systematic studies, especially for metallic lattice structures. And a bit background about the lattice structures. So there are several categories we can classify. So first, we say this is a Voronezh lattice. So it has an application for the footwear and the muscle tissue modeling. And also we can classify the lattice as the surface-based. And there are several applications for this type of lattices as well. For example, the heat exchangers and lightweight structural components and energy absorptions. And also there's a struct-based lattices. So for this type of lattices are more famous for the biomaterials and biomedical implantations. And also it can use for the high performance gear as well. So for let's jump to the materials and the methods. So for this, all the specimens are fabricated via aluminum silicon magnesium powders with the laser powder bed fusion powder. And the layer thickness is 30 microns, and also the maximum power is 350 watts, with also the CT scan were used for that. And for all the geometries, all those specimens were classified into the 3 categories. So first, it is the scale effect, but by keeping the constant relative density for all the lattices, but varying the unit cell size and the wall thickness. So the second will be the unit cell size effect by having the constant wall thickness. So basically changing the unit cell size, but keeping the constant wall thickness. And also the third category is the wall thickness effect by having the constant unit cell size, but changing the wall thickness. So basically all the parameters of the lattice structures have been investigated comprehensively in this case. So there are some naming rules and dimensions for this for all the specimens. So the cubic size we chose is all the way from 8 millimeter to 42, and according to and also corresponding to different unit cell size. And we use the names as G stands for gyroid, X stands for unit cell size, and the 1 stands for wall thickness. So in this case, by looking at the name of the lattice structure, so we know all the parameters details. And also these are all the detailed parameters, as we can see the highlighted numbers here. The geometric dimensions here, for example, 8, lattice name here, the second number is 2. So which means for all the cases, actually this number for the geometric dimension is always 4 times larger. So which indicates that for every specimen, there are 4 unit cell size on 1 dimension. And this is all the detailed parameters for all the classifications. So as we can see, for the first scale effect, all the lattices have the same relative density. And for the second one, unit cell size fact with the same wall thickness, and the third one with the same cubic size and unit cell size. And please note that the specimen in the middle is actually when we categorize that, it can be categorized used for 3 times. So in total, there are only 7 specimens or 7 geometries were fabricated. And go to the results and discussions. So first, the geometrical accuracies and deviations were discussed here. So this is a typical views. So as we can see, the red part indicates the excessive particles and the materials on the lattice structures, and the blue parts indicates the lacking of the materials based on the geometry of the lattices. And all the geometries have been went through all the CT analysis, and we can see that for example, the scale effect, as the scale increase, the percentage of the deviation also decreases a lot. And if you look at the numbers here, this is actually the lattices with the smallest dimensions. It has a huge deviation of the percentage. And also, we also calculate the actual surface area to volume, and most of them has the similar trend as the percentage of the deviation. And also we can see for this lattices with the wall thickness effect, the lattices with the thinnest wall thickness has also the largest percentage of the deviation in this category. And also internal porosity analysis will also determined in this case. And here we use the CT scan to determine all the layers of the lattice structures, and this area represents the cross-sectional area. So as we can see, there is a huge deviations between the scan and the CT files of the areas, and this is the lattice with the smallest dimensions. And also there's internal pores here. And the reasons why this has the fluctuating trends is because of the boundary effects of for each layers. And also this from the file, we can see that the red dots indicate the pores, and this is for the specimen with the smallest geometry. And if we compare the internal porosities with the geometrical deviations, here we have a lot of data, but if you look at the highlights here, as we can see, as the scale increase, that the percentage of the deviation decreases significantly. And also, if you look at the area of the internal pores, actually for the for the lattice with the smallest dimension, and also the second one, it has a lot more pores than compared to the rest. And if we compare the internal porosity with the geometrical deviations, most of them, some of them shows the similar trend, but some of them shows the opposite trend. And for the geometric deviation, we can see that as I stated, the lattices with the smallest dimension, also the lattices with the thinnest wall thickness has the largest deviations here. And this is the quasi-static compression. As we can see, some lattices has the shear band after compressing to certain strengths, and some of them don't. And if we, this is related to the stretching dominated and bending dominated behavior. And if we compare the stiffness and the yield strength of the actual lattices, and compared to design, we can see the deviations for the lattices with the smallest dimensions, and all of these deviations are caused by the geometrical accuracies. And the photography analysis will also performed on the lattices here. And also this is for the fatigue loading conditions. The frequency was 20 Hertz, and the load failure condition was 80% of the original height, and the runout cycle was 2 million. And as we can see here, the surface on the top side have overhang areas are much smoother than the bottom side. So it depends on the geometry of the specimens, the fabrication quality is really different. And also the crack initiated from the rough surface and propagated through the thickness. And also most of the fractures occur close to the center of the fracture surface. And also the specimens with the smaller thickness tends to have fewer cracks according to the observations. And this is the fatigue strength plotted. And here we have the designed relative density, and we have the actual relative density based on the CT scan. And as we can see from the data of this table, we can see that for the actual fatigue strength, as the thickness increase, the actual data has a clear trend of increasing and of 63%. And this is one of the reasons can be attributed to the fact of the surface to volume ratio is decreasing as the wall thickness increasing, as I previously presented. And also, if we compare the fatigue strengths with based on different categories, we can see that the fatigue limit decrease when the scale increases due to the decrease of the relative density. And also, the fatigue failure is highly sensitive to the localized deformation. And also, the increase of the scale leads to shear bands under the quasi-static compression. And the fatigue is mostly governed by the nature of the deformation. Even in this case, surface roughness also played a role, but it's not as important as the nature of the deformation here. And also the fatigue limit decrease when the unit cell size increase, as in the lower relative density. So also we have the normalized stress versus the fatigue life here. And we have the maximum stress, and now we have the normalized stress. So we can see that the fatigue data is normalized with the yield, and it's solely governed by the nature of the deformation. And we can see that the two geometries with the smallest unit cell size shows the largest deviation, and the normalized stress follow a very similar trend compared to the stress without the normalization. So by conclusion, we can conclude that the opposing trend between the manufacturing accuracy and the scale were observed at the range from 10 to 90%. That's quite a lot. And the relative density decreased with the larger scale and the unit cell size, but increased with larger wall thickness. And also because of the geometric increases raises for both relative density and wall thickness. And the monotonic behavior for static compression also shifted from the stretching dominated to bending dominated. And the strong correlation between the fatigue and the scale can observed. So the factor of increasing R5 lead to a fatigue data strength by 22%. And the relatively lower cycle fatigue show the different crack propagation, the different crack patterns than compared to the relatively high cycle fatigue. So the relative high cycle fatigue show the crack initiation from the both centered and edged, while have the minimal barrier effect. So thank you for your kind attention.